So in the previous video, we saw cardinality, and we saw a simple way of getting an estimate for the cardinality simply by hashing all the input items, taking the minimum hash, and then plugging it into a simple equation. So in this second video, we're going to do two things. First of all, we're going to bring a little bit more rigor to that equation that we used, that we plugged the minimum into. And then second of all, we're going to talk about what we can accomplish by taking not just the minimum, but more than one representative from the data set. More than just the minimum, maybe the minimum, the second minimum, the third minimum, and so on. Okay, so reviewing what we said at the end of the previous video, we said we are going to treat the hash function as something that's allowing us to spread out the values of, the hash values for the items in the data set. And whereas we normally think about the hash function as putting them into slots, now we're going to think about them as just spreading them out from 0 to 1. In other words, if we just take the hash value, the unsigned hash value might be an unsigned 64-bit integer, and just divide it by the maximum possible value, we'll end up with results that vary between 0 and 1. So we can think of the hash function and the randomness in the hash function as our sort of adapter for taking any data set and turning it into and taking all of its items and mapping them on to random spots between 0 and 1. And now we have a setup that's just like the hat problem, the problem where I have the numbers in my hat, a random subset of the numbers in my hat, and you can ask for one representative. And we said that a good choice was to pick the minimum. Okay, so whereas in the previous lecture we saw this, we took the the number on the smallest card in my hat and plugged it into an equation that looked like this, where we had to know, basically how many slots there were, how many possible values there could be on those cards. Now let's just adapt it so that instead of this line we have the 0 to 1 line. And so maybe I took the minimum hash value among all the hash values of all the cards in my hat, or all the items in my data set, and maybe that minimum hash value was 0.095. Now I plug it into this equation where I have 1 over big N plus 1 on the right-hand side. Just like we were doing before, but we sort of made it continuous, where the hash values can be between 0 and 1. Okay, so now let's come up with a random variable that's going to help us to model what we have on the right-hand side of this equation here. It's going to help us to understand that in terms of the expected value of a random variable model for this problem, the hat problem. Okay? So let's define a random variable, big M, and let it be equal to the minimum, so the representative that we would like to pick from among all the hash values. So that means I need these random variables, these big X's, to represent the results of applying a hash function to each of the items in the set. So we're saying, even though big N is an unknown, right, big N is the number of items in the set, so I'm going to just write down a big X for each of the items in the set. And the big X is simply, we're modeling a uniform draw from real numbers from 0 to 1. This is just our way of modeling what the hash function is doing. It's like for every key we draw a random number between 0 and 1 and map the key to that number. Okay, so these X sub i's model the hash values for those N items, and the random variable big M equals the minimum, the representative that we are keeping, so that we can estimate the cardinality, or big N. Okay. And so the claim here is that the expected value of this random variable, big M, is the size of one of those partitions, right? So we said the N items partition up the interval from 0 to 1 into N plus 1 partitions. So we would like to argue that the expected value of big M is the size of one of those partitions, 1 over N plus 1, which would justify the way that we were estimating the cardinality from the minimum item. Okay, so let's work our way toward this claim. And it'll help to think of a concrete scenario where we actually do these random draws, and we think about what is big M given the random draws being given to us by the big X's, by the X sub i's. So let's draw a little diagram. Let's say here are my draws. I'm drawing them like they're sort of elements in what will become a sort of table. So I've got my draws for item 1, item 2, item 3, all the way up to item big N. And those are my big X random variables. And of course my big M random variable is the minimum from all of them. And I'll define a parallel set of random variables that are indicators. So what's the indicator going to tell us, or what event is it tied to? It's tied to whether the big X that it corresponds to is the minimum among all the big X's. So I've got a parallel set of indicators, I sub 1, I sub 2, I sub 3 up to I sub big N, where the indicators are, an indicator like I sub 1 is 1 if X sub 1 is the minimum among all the draws, 0 otherwise. Okay, so I sub I, big I sub little I, equals 1 if the corresponding big X is less than all the others, 0 otherwise. And the way I've chosen to say that X sub I is less than all the others is just X sub I is less than minimum over all possible j's not equal to I of X sub j. Now, because we're in this continuous case, we're sort of assuming that the hash function is giving us effectively continuous values from 0 to 1. We can ignore collisions for now. So we're going to ignore the idea that there might be a tie for minimum. Okay? So now let's think through a concrete scenario where we can just, let's pick I equals 5, or sorry, big N equals 5. So there's X sub 1, X sub 2, X sub 3, X sub 4, X sub 5, and the corresponding array of indicator random variables. And let's just fill in sort of a random way of picking these X sub i's. Fill in some random numbers between 0 and 1. Here they are, 0.455, 0.220, blah, blah, blah. And what do I have to write as the values of the indicators? Well, I have to write 1 if the indicator corresponds to the minimum among all the X sub i's, which this one does, right? So I sub 2, which corresponds to X sub 2, is the one that's equal to 1 because 0.220 is less than all the others, okay? The other indicators are all equal to 0. So this is scenario 1. And in scenario 1, big M, which we define to simply be the minimum of all the big X's, is going to be 0.220. So now let's add in scenario 2. So here's scenario 2. New set of random numbers here for the X sub i's. Once again, this one ended up being the minimum, 0.234. So that indicator is the one that gets 1. The rest of the indicators get 0. I've got a new arrow here pointing where the scenario 2 big M is, which is just a little bit to the right of the original, of the one from scenario 1. And let's just get a third scenario. Okay, new set of numbers. Let's see. Now this one is the minimum, 0.143. So this indicator is 1. The rest of the indicators are 0. And I have my new arrow here. You get the idea, right? The random scenario that our random variables are helping us to sort of play out is that all the X sub i's get some random number from 0 to 1. One of them is the minimal one. That one, therefore, gets 1 in the corresponding indicator random variable. The rest of the indicators get 0. Okay? So the interest in playing out all these scenarios is going to be that the expected value of the indicator is going to be important to our analysis. So the expected value of the indicator will be important. And now let's create the link so that we know what to write down as the expected value of the indicator. But we need to sort of go beyond the big N draws that we're doing and add one more, a hypothetical extra draw beyond the nth draw. So let's just sort of color that in. So here are our X sub 1, X sub 2, X sub 3 up to X sub N. And then here's a hypothetical next draw, X sub N plus 1. it's not really part of our problem setting, right? There are only big N items in the input data set. That's why I'm calling it a hypothetical extra draw. But it'll be useful for the analysis. And likewise, of course, there's an extra indicator here. Okay? And this extra draw is, just like all the other draws, is a draw uniformly between 0 and 1. And this extra indicator has the same meaning as the other indicators. It's equal to 1 if the corresponding draw is minimal. Okay, so let's think about what's the expected value of one of these indicators. So if I run this scenario that you see here, I'm going to do these n+1 draws, and I've got my n+1 indicators. What's the expected value of one of the indicators? Well, it's just the probability that that indicator equals 1, which is the probability that that draw is the minimal one. Okay, so, but by symmetry, right, all the draws are equally likely to be the minimal draw, right? There's nothing special about any one of these draws, any one of the n+1 draws. So the expected value of an indicator is just the probability that that corresponding draw is minimal, which is going to be uniform across all the draws, even for all the draws. In other words, it's going to be 1 over n+1. Okay? So in this hypothetical scenario where we do n draws and then an extra n+1th draw, we have that the expected value of an indicator is 1 over n+1. So let's just write out what we're saying here. 1 over n+1 is the expected value of any of the indicators. Let's write this as the expected value of the n+1th indicator, right? It's true for all the indicators. But let's just write this as the expected value of the n+1th indicator, right? So for that, that's the probability that right, just by the definition of this indicator random variable, right, it's equal to 1 when the corresponding draw is less than all the other draws. So the expected value of the indicator is the probability that x sub n+1 is less than the minimum of all the others. Let's say 1 less than or equal to I less than or equal to big N of x sub I. Okay? And then let's think about what that is. Let's say that this right here is the minimum of all the draws except for the n+1th, right? So all the draws from, excuse me, I needed to do 1 less than or equal to I less than or equal to n of x sub I. So let's say that this right here, let me use another color, this right here is the minimum among those first n big X random variables. This probability, the probability that the n+1th is less than, is just basically exactly what we're looking for. It's the width of one partition, right? So this probability, the probability that the n+1th draw is less than all the others, is nothing but the expected value of the minimum. The expected value of big M, that random variable that we defined at the outset. So let's pause for a second and think about what we've been doing. So we now have an equation that links up the expected value of that random variable big M, which is the minimum of all of the x sub i's from 1 up to big N. And we're saying that we were able to link that to the value that we were using to estimate the length of one of those partitions, the 1 over big N plus 1. So when we take the hash values of all the input items and we find the minimal hash value among all those input items, and then we use that to calculate the cardinality, by way of the width of one of the partitions, essentially what we're saying is the minimum hash value is our best guess for the expected value of big M. Remember what big M is. It's the minimum of n random variables, and we don't know what n is. So this is all a process of trying to get back to what n is. And the best guess that we have is the minimum hash value. The best guess we have is to use the minimum hash value as our best guess for expected value of big M. But it seems like maybe we could come up with a better guess, right? I mean, this is just one of the values from the hat. And it doesn't feel very comfortable to just use the minimum among the hash values from the hat, among the cards from the hat, right? Because you might just, by coincidence, you might get a value, for example, that's very, very close to 0. You could get indeed, you could get arbitrarily close to 0. And the closer you get to 0, the more your estimate for the cardinality is going to blow up into potentially a very large number. It would seem to be a safer bet if we could use more than one of the cards from the hat, more than one of the minimal hash values. So let's think about how we could do that and how could that help. So let's say, just to generalize a little bit, that instead of taking the minimum value from among the cards in the hat, or from among the hash values from the data set, we take the kth minimum. What do I mean by kth minimum? Well, instead of taking the minimum, we could take the second minimum, or the third minimum, or the fourth minimum. And I'm just using the variable k to represent that we can pick. You know, we can pick how far from the bottom of the list we're going to go in terms of taking the minimum. So just to visualize this, here again is my range of hash values 0 up to 1, and let's say the minimum is right here. Well, maybe the second minimum is there, and maybe the third minimum is there, and then dot, 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 maybe the kth minimum is there. And so we're going to think about what does it mean if we use the kth minimum value instead of the minimum value. And you might be thinking to yourself, well, that doesn't sound any better, right? Because either way, whether we're taking the minimum or we're taking the kth minimum, we're still just taking one representative from the hat. So how does that help that we're getting the kth minimum instead of the minimum? Well, let's think about that. So first of all, let's change the notation so that we don't have to keep saying kth minimum. Let's switch to using these symbols. So big M subscript 1 here is nothing but the minimum. That's basically what we called big M before. So big M sub 1 here is what we called big M before. Big M sub 2 is the second minimum, sub 3 is the third minimum, sub k is the kth minimum. Okay. So we know that the expected value of the minimum of all the random draws, so M sub 1, we called it M before, but we're calling it M sub 1 now, is 1 over n plus 1, 1 over big N plus 1. Okay, we showed that. So the expected value of big M sub 1 equals 1 over big N plus 1. Now let's think about what's the expected value of big M sub k. Okay, well, if the expected value of big M sub 1 is the size of one of these partitions, one of these k plus 1 partitions, then the expected value of M sub k ought to be the size of k such partitions, the total size of those k partitions. So instead of putting 1 over n plus 1, I'm going to put k over big N plus 1. Okay. So obviously, if you tell me the kth minimum value, if you tell me your best guess for big M sub k, I can turn that into an estimate for n, right? I can use this equation, solve for n, and now I can estimate big N from your big M sub k. Okay? So my point about this, so the answer to the question, isn't that just another point on the line, is not quite, because what it's allowing us to do is to get at the size of a partition, but by taking an average of k partitions. Instead of just taking the length of one partition, we're now able to estimate using an average of k partitions. And this is going to help resist against the sort of wild fluctuations that we might get if by coincidence we got a hash value that was not very representative of the average partition length, right? So it's helping us get closer to a stable estimate for the overall cardinality. Let's see what I mean when I say that this is an average. First of all, let me just point out that we could also write it this way: expected value of big M sub k over k, I'm now just dividing both sides by k, equals 1 over n plus 1, okay? That makes the average nature of it a little bit clearer, but now let's make it even clearer on the next slide. So again, 1 over n plus 1 equals expected value of big M sub k over k. And the point I just want to make here is that big M sub k, right, is this length. It's the length from 0 all the way up to the kth minimum, this whole thing. But of course, that whole length is nothing but the sum of the lengths of these individual partitions between the minima. So in other words, if you want the length of this whole thing here, let me draw it like this. If you want the length of this whole thing here, you get it by taking the sum of the little ones from 0 up to m sub 1, and from m sub 1 up to m sub 2, and m sub 2 up to m sub 3, etc. Right? So the length of the range that goes up to big M sub k is nothing but the sum of all these smaller ones. And so that's what tells us that we can think of this as an average. So we can write it this way, right? That the expected value of m sub k over k is like, first of all, look over here, I'm multiplying by 1 over k, so that takes care of the over k part, right? I put that on the outside. But inside here within these square brackets, I just have all of the individual partition sizes, right? I'm just adding them all together. All right? And this whole expression is equal to this. In other words, the expression that we're using when we're taking the kth minimum and plugging it into this equation, where the expected value of the kth minimum equals k over big N plus 1, is we're essentially taking k partitions, averaging them, and using the original way of turning a partition length into an estimate for the cardinality. It's just bringing averaging into the method. And so this approach is called kth minimum value, this approach for estimating the cardinality from the kth minimum hash value. Kth minimum value, or Kmv, and it essentially just averages the k estimates for 1 over big N plus 1. And just to show this in action, here's sort of the result of a simulation experiment. What I have here along the horizontal axis is I just did 1,000 random trials of these different methods, and so the different points along the horizontal axis are just the results from those 1,000 random trials. This y-axis here is telling you if I use these different methods to estimate the cardinality, what estimate do I get? All right, and so higher is a bigger estimate for the cardinality, and lower is a lower estimate for the cardinality. And the true cardinality is drawn in there in black, right? It's this line right here. That's the true cardinality. So in my simulation, I set the cardinality to be 1,000. And I'm using 3 different approaches. I'm using the approach where I just take the minimum, so the very first thing we talked about. Then I'm doing kth minimum, but for 2 different values of k, 10 and 100. Okay. So if I just use the minimum, I get estimates corresponding to these red points, which, as you can see, are sort of all over the map, right? Some of them are very high, you know, way too high, corresponding to that situation that I was talking about before, where maybe our hash value was so close to 0 that when we plug it into the equation, we end up getting a blown up version of an estimate for big N, right? So these red dots that are up here are showing that that is indeed happening sometimes. These blue rings, which correspond to 10th minimum, as you can see, seem to be forming a tighter, like if I just draw a line, I think all the blue dots pictured are below that line, and all the blue dots pictured are above this line, right? You can see they're sort of in a tighter range with respect to the true cardinality of 1,000. Then green now is the 100th minimum value. We're taking an average, but now we're averaging 100 partitions instead of 10 or 1 partitions. And now you can see, indeed, it's pretty tight. I'm just going to approximately draw. That is the range that they all fall in. Okay, so you get the idea that as we get more and more averaging, we get a tighter and tighter estimate. All right, we're less and less likely to blow up, essentially get a ridiculously high or low estimate for the cardinality. Okay, so one quick point before I move on from kth minimum value. Kth minimum value, even though what comes out of that kth minimum value procedure is just that kth minimum, right? We're not necessarily keeping, for the purpose of performing our estimate, we're not necessarily keeping the minimum and the second minimum and the third minimum. We might be just aiming to keep the kth minimum, and that's it. However, in order to calculate the kth minimum, we do need all those other smaller minima right? Because how do I know I'm the kth minimum if I don't know what the k minus 1 smaller ones than me are, right? So the process of calculating the kth minimum involves having calculated smaller minima than that. And so although it would be kind of a waste of space to keep all of them around 2 if all we were intending to do was to estimate the cardinality, there may be other reasons, as we'll see, why we would want to keep all those minima around. Not just the kth minimum, but the k minus 1, k minus 2, all the way down to minimum. Okay? And one more thing I'll say is that obviously because we're trying to find the kth minimum, that's harder computationally than just finding the minimum. Like we said before, finding the minimum is just really drop dead easy, right? I just take the minimum so far and I do something very simple to update it each time. With the kth minimum, it's more difficult because if you imagine now one item has come in from the stream, I need to figure out, is it the kth minimum? Or is it the k minus 1th minimum? Or is it the k minus 2th minimum? Or is it the minimum? And then I need to figure out, therefore, where I need to insert it. First of all, it might be greater than the kth minimum, so we don't care. But if it's less than the kth minimum, I need to figure out where to insert it, such that I can now have an updated view of what are the kth minimum values so far. This is more complicated than if we are just trying to keep track of the minimum. So we're definitely paying in terms of it being a little bit more complex computationally. We're not necessarily paying in terms of the final number that comes out. We might just keep the kth minimum and throw all the other minima away. But keep in mind, as we'll see, there will be situations where we wish we did keep all the k minima around. Okay, so I want to conclude this discussion of kth minimum value by talking about a couple of alternatives. You know, kth minimum value is appealing because there's really only one hash function here, right? We're just using one hash function, and we are keeping track of the, obviously, of the k minimal values from the stream as the stream goes by. But there are a couple of other ways we could do this, one of which still just uses one hash function but does it differently, and then another one that uses more than one hash function. So let's look at those. Okay, so again, what we've essentially done, this is sort of the Kmv method, right? The kth minimum value method. In this particular example, I guess k is 7, right? 1, 2, 3, 4, 5, 6, 7. So this is like when we're doing kth minimum value where k equals 7, let's just say these purple triangles correspond to the k minimum values. Those are the ones that we find, right? And therefore, you know, this one might be the one that we actually plug into the equation, right? When we say, you know, that equals that being the expected value of m sub k equals k over n plus 1, right? We plug 7 in for k. Okay, so tracking up to k minima squeezes more estimating power from a single hash function, right? We have not increased the repertoire of hash functions. There's still only one, but we are increasing the number of representatives that we're taking, that we're considering when we're coming up with our summary. It's like asking for more than one card out of the hat. But there's another way to imagine doing this. Instead of taking the minimum k from the entire range of the hash function, let's first divide the range of the hash function up into k partitions, like this. So what have I done here? I just have these black lines indicating this is a partition, this is a partition, this is a partition. There's 7 of them. And now, instead of having to consider more than one minimum from any given partition, I'm just going to consider the minimum in each partition. Okay, so let's say these purple triangles correspond to the minimum hash value of any item from the data set among the possible hash values in that partition. In other words, of all these possible hash values, the one that was in my data set that was minimal was this one. And then among all these possible hash values, the one in my data set that was minimal was this one, and so on. Okay, so what we're saying here is we can partition the range of the hash function k ways, let's say just k equal partitions, and then we find the minimum value within each, and this again gives us k estimates for the width of one of those partitions, one of those 1 over n plus 1 partitions. So again, we can use averaging, right? So we have k different estimates for that interval length. We can average them, then we can plug them into the equation to get the estimate for cardinality. Conceptually is extremely similar to what we were doing up here when we were taking the kth minimum. Okay, so that's another idea. And then yet another would be, let's go ahead and use more than one hash function. So building on that k partition idea, instead of taking one hash function and dividing its range into k partitions, let's just use k hash functions and not divide their ranges up at all. Let's just use k different hash functions. So here's one, and then here's a bunch more. So here's 7 hash functions, and I'm just using different colors to show that they're putting the items from the data set in different orders. But the point is, from each of them, I'll again calculate the minimum. So every single item that goes by from the data set, I'm actually going to, for each of these 7 hash functions, I'm going to use all 7 of them. I'm going to come up with 7 hash values. And for each hash function, I'm going to ask, is this the minimum hash value I've had from this hash function so far? If so, I update. Same thing for the other 6. So I'll end up with these 7 minimal hash values. Again, each of them is giving me an estimate for that interval length, 1 over n plus 1. So I can average them, and then I can turn that into an estimate of the cardinality just as before. And so just as a bit of vocabulary, the initial idea that we had of taking the kth minimum hash value is what's sometimes called a bottom k approach. That second approach, where we took the range of the hash function and divided it into k partitions and then found the minimum hash value within each partition, is sometimes called k partitions. It's also sometimes called one permutation hashing. And then this other approach, which you can sort of think of as being the generalization of the other 2 approaches. You can think of the other 2 approaches as being optimizations that try to get away with just using one hash function. But you can always, of course, use k different hash functions, which I'll just call a k hashes approach. Okay? All of them benefit from averaging, right? The whole point of doing something other than the hat problem and just taking the minimum with a single hash function, the whole point of going beyond that is we want a better way of estimating that expected value so that we are plugging something better into that equation and getting a better estimate for the cardinality. All of these benefit from that averaging. But the 2 on the bottom, computationally, are often more convenient because they both only use one hash function. There's caveats that come with that, a little bit more detailed for this lecture, but in practice you'll find people often doing one of these 2 approaches. Okay, so to conclude, we're about to move on to talking about min-hash and about sketches in a broader sense. So, but kth minimum value has been a nice bridge because what it showed us is that even for this simple problem, where we're just trying to estimate the cardinality of a set, we can get a better estimate by looking at the kth minimum value, considering k of the minimal hash values from a data set instead of just the minimum. So keeping the k minimal hash values is also a sketching strategy. It's essentially called it's related to what's called the bottom k min hash strategy, which we're about to see, and it's the basis for a lot of sketching strategies in general. So if we think of sketching as being like the task of taking a very high information content data set and turning it into sort of a special version of that data set where we've deterministically kept particular hash values from that data set. Again, not the same thing as random sampling. It's a kind of deterministic intentional sampling of certain points. Then what we're doing with kth minimum value, let's say the input is some text, and we're putting it through essentially a hash function and taking the k minimum values, which themselves are some numbers, right? You can think this is a way of taking a text, making it much, much smaller, and yet we're still able to do at least one interesting thing, which is to estimate the cardinality, the number of distinct items in the data set. And next, we'll see how to use these same sorts of things, these sketches, to find the degree of similarity between data sets or whether one data set is contained within another.